your head is this whole pantheon of different matrix factorizations that we've covered. Everything from LU, QR, Cholesky, lower triangular matrices, upper triangular matrices, and so on. The basic idea is depending on where you are in life, you may have one or the other of these systems. In particular, equations that we really like are symmetric and positive definite, and there was one case where this comes up all the time, and that's when we solve this minimization, minimizing the norm of ax minus b squared, right? And we have exhaustively gone over every possible case when a is short, when a is tall, when it's overdetermined, underdetermined, and so on. And it's important to go over and understand when you use these tools and what they can help you with. Obviously, I also like asking you guys some model problems using these tools rather than just reinvent algorithms we already know. So that was sort of part one, right? We did that, we covered some eigenvalue problems, and most importantly, at least in my view, we went over some applications of like when you might use this machinery, right? Your homework has gone through problems of machine learning, graphics, interpolation, and so on, many of which just boil down to basically out of the box the algorithms that we've covered in class. Yeah? So in part two, we moved from linear problems to nonlinear problems, and in the first couple weeks of the second half of the quarter, we did sort of what would fall under the big umbrella of optimization and analysis, right? So we started with root finding and optimization, and in fact those two sets of algorithms have a lot in common because optimization you can think of as root finding on the derivative of a function. It's a lot of words, but it actually makes sense, right? Because how do we minimize something? We take its derivative and we set it equal to 0. So these are very closely linked problems. Okay? The types of issues we have there is, well, for one thing, we don't even know that our problem has a solution necessarily, but more importantly, it can be difficult or very expensive to evaluate derivatives, invert matrices, and so on in these iterative methods, and we'd like to make sure they converge quickly. After that, we returned for one more reprise of ax equals b in conjugate gradients. By the way, I updated. I made a small math mistake in our discussion of CG in class, which was clear if you were in that lecture that I made a mistake. And I fixed that in the course notes. Technicality. But right, the idea here is you have a really big system of equations. You might not want to invert that matrix, especially if it's sparse. One of these things you should keep in your head, just like A transpose A squares the condition number, remember that one? Is that the inverse of a sparse matrix isn't necessarily sparse. Right? So if I do LU factorization on, for example, that nice -2, 1, -2, 1 matrix I've been writing down on class today, the inverse of that matrix, you can try it in MATLAB, is very dense. 100% dense, in fact. And so in that case, we might want to use tools like conjugate gradients that don't necessarily give me the exact solution to ax equals b, but slowly can, well, perhaps quickly converge on that solution in a nice iterative way that only requires matrix multiplies, right? Instead of matrix inversion. It's a nice property. And then the last couple weeks of the class, we covered problems where your unknown is a function rather than just a number or a point, right? So for root finding, your unknown is still a point, right? It's a point in Rn that minimizes the function. But now we're going to say maybe we want to solve, for example, a differential equation, and your unknown is a function that satisfies that boolean. Yeah? And so we have different methods depending. The intuition you should have is that somehow a variable that looks like time is very special. And a variable that looks like space is also very special in a different way. And you have to decide how you want to treat these two things, how they're linked together, and so on. And that the story in ODE and PDE is a little weird because your differential equations, you need to check that theoretically they're solvable, that theoretically they're well posed, and also that your discrete method will give you the solution you want. So for example, if you do forward Euler with a big time step, it's just going to give you garbage. Yeah? And so we have all these time step restrictions and so on. So in general, there are kind of two roles, and you'll see these in equal play on your final exam. One is as a kind of a client of numerical methods. For example, how to take some problem from a field or another, whether it's computing disease spread or some machine learning thing, and then just fitting it into one of the boxes we've covered. And then also, how could you design a new numerical method that's kind of a variation on something that we've seen in this class. And both of these are very important roles, and depending on what you do. And in particular in this class, right, one vocabulary word which perhaps isn't quite as common for numerical analysis classes is that we've tried to take a nice variational viewpoint, right? So almost any time we don't know how to solve a problem just algorithmically, I said, well, rather than solving it algorithmically, just write down some energy that measures things you like, That is, the energy function is somehow small when your answer is good. Right? For example, the norm of AX minus B. Right? And then we'll use some out-of-the-box tool to minimize that. And this is a very common pattern, and one that you guys should be very good at applying by now. We've done it almost every single homework. Yeah? All right. So in about 30 seconds, a lot of people have emailed me about what's next, and if you have questions about other classes, I've been at Stanford now for at least 8 years, and have gone through many of these classes myself, and also have tutored people on understanding textbooks and so on. So if you have questions, in general, almost anything in the CME department will be an extension of what we've done in 205A. Basically, for each week in 205A, there's an entire course in the CME department that covers that 1 week in more detail. And I highly recommend you take classes on things like differential equations, and in particular, the course on convex optimization is really good here, and you should not leave Stanford without taking it. Within the computer science department, there's everything from vision, machine learning, graphics. I noticed that there's another, the convex optimization course is now in the CS department too, which should underlie the fact and how popular it is. But anyway, if you have questions about that, please let me know. So, one final reminder, your final exam is cumulative. It has a similar format to the midterm. You get 2 sheets of notes, and it is in Gates B3. It is not in this room. It is in Gates B3. Okay? And with that, I think we'll stop. So it's really been a pleasure to talk to you guys. I appreciate your patience this quarter. I've learned a lot, and I hope you have too. Hopefully I'll see you in office hours before your final. And yeah, good luck with the rest of the quarter. Thanks, guys.
Will there still be office hours next week?
I will hold office hours. The hours themselves might be different, so I'll post this.
Okay.